Okay, so welcome everyone to today's question and answer session. So we will kind of first go through the tutorial that was posted yesterday, and after that I will, we will take up your questions. Okay, I'll switch off the video now and then share the tutorial 5. Okay, is the tutorial visible now to everybody?
Yes, sir.
Yeah. Okay. Excellent. So this tutorial this time it is kind of very straightforward, very simple, because we have already discussed Jacobi iteration in the lecture on I think on Thursday's lecture we discussed Jacobi iteration, as well as we looked at the corresponding kind of code fragments as well, right? So it should be very straightforward. So essentially you will be working with a system of linear equations A is equal to B. And then where x is the unknown vector to be determined and b is the right hand side. You can choose any right hand side vector that you like, whereas the matrix A is tridiagonal and the coefficients are basically given as on the primary diagonal are all 2, and then on the sub and super diagonals are -1 and -1. Okay, now the idea here is that because this is an iterative method and we are working with only a tridiagonal matrix, you will not allocate a matrix A. Okay, you will not work with the matrix A. Rather, you will only work with the corresponding equations that we have derived, right? So from here, you can derive the equation that is in terms of xi minus 1, plus 2xi or minus 2xi, and then plus xi plus 1 and so on, and then with the right hand side. So you will only work with those equations, and then you will find a solution by performing a certain number of iterations. Okay. Now, you can also modify the code to include instead of iterations, because we cannot guess how many iterations are required. You can even include to have certain epsilon. Okay. So for the solution to kind of converge between two iterations, if the difference is less than certain epsilon, which can be 10 power minus 4 or minus 3 or some norm, you can implement that as well after you are done with implementation of iterations. Okay. So that's the kind of description of the problem. So one program you develop would be the sequential program. That should be very straightforward for solving the system of linear equations. And then you can assume a suitable RHS vector. You can develop either in C, C++, or Fortran. That is fine. Then you will now extend this sequential code to an OpenMP version. Okay, by adding the OpenMP directives as required. And then you would actually run the serial and the parallel programs. Okay, you can probably use 2 threads or 4 threads and see whether you are getting the same result from both the programs or not. That is the first step. Okay, so once you convince yourself that your program in parallel is running fine for a different number of threads and it is giving the correct answer, then you can go ahead and increase the number or size of the system from a 10 by 10 matrix to a very large matrix, so that you will probably start seeing some performance improvement between the serial and the parallel versions. Okay, so that is the idea of the tutorial. I think it should be very straightforward because it's already discussed in the lecture. Okay. All right, so that is about the tutorial. I think many have now joined. I would like to make a few announcements. So I'll post your, we will post your assignment 1. Okay, that's most likely will be based on what we have done till now, and then something that we will do next week. So assignment 1 will be posted by Monday. Okay. So that is Monday would be 8th. Okay, 8th of March I will post by Monday. And then you would get approximately a couple of weeks to work on it. So you can submit by most likely by 22nd. Okay. So deadline will be 22nd. It will have 1 or 2 problems, so you can easily do that in the given time frame and then submit. I will be asking you to submit a zipped code folder that you would develop, as well as whatever is the the results as a or any other hand calculation you do, or the results you get in terms of graphs or whatever is required. You would upload them on Moodle. I will create a submission link. So you would basically upload a PDF file plus a zipped code folder that you would kind of develop. Okay, so that's your assignment 1. That will basically cover, whatever we have discussed till now, essentially OpenMP plus the numerical methods that is ongoing. Okay, and then another announcement is, okay, we'll have our quiz 1. So quiz 1 will be on next Tuesday. That will be on 16th. Okay, so your quiz 1 will be on Tuesday, 16th March 2021. Okay, this will be in lieu of your lecture. So on Tuesday there will be no lecture. Rather, we will so essentially the question paper will be posted by slightly before 11 o'clock. So the exam will be from 11 a.m. to 11:50 a.m. Okay, just like your regular quiz. And then what you would do is, once the question paper is posted on Moodle, you would download it, write it on a nice piece of paper, probably nice A4 sheets, and then scan them nicely, your solutions, and upload them. Okay, I'll give you some 15 minutes or so to scan and upload after the exam, so that I'll get answer sheets uploaded from everybody. I think this is preferred because hopefully you don't have a class after this or something, so you will have enough time to scan and upload. Because on other days you might have a class following our lecture. Okay. So the question paper, I don't know about the kind of questions will be set, but most of them will be essentially you will probably comment on something, or you will essentially explain how something works, or how what is the problem in a given code or fragment or something like that. Some questions will be like that. I mean, essentially it's just a 50-minute exam covering the first 3 chapters, that is introduction, OpenMP, programming in OpenMP, and numerical methods in OpenMP. Okay, so that would be the syllabus. Using OpenMP. Yeah. Okay. Okay, so that would be the syllabus. And in order to help you to kind of get prepared for quiz 1, what we will have is, so next week, that is on 12th March, so next Friday. So 12th March would be kind of the session will be, I'll probably not give a tutorial, or maybe a very simple tutorial, but then 12th March would be, we will do a preparation for quiz 1. Okay, I will see if I can somehow prepare you, so that you will be in a better position to write the exam. So we'll do preparation. That means some sample questions, or something like that I will prepare, and then of course you can always ask questions, and then we will answer them. So that will be the plan going ahead. Okay. And of course, we also just heard from the dean that there will be 1 week of no lectures, I think from 27th March to 4th of April. So we have to make up for that little later. Okay, all right. Yeah, okay. So that's all I have to say about the tutorial and the announcements. Yeah, so let's see if anybody has any questions on the lectures, as well as on the on whatever I just discussed in terms of regarding assignment and quiz and things like that.
Yeah, hello. Am I audible?
Yeah.
Yeah, the thing is, I don't have access to a scanner nearby. It'll take me about an hour to get it scanned outside. So is it okay if I have an app on my phone that I can, through which I can scan?
You should be using only your app on your phone. You don't have to go to a scanner.
Okay.
Yeah. You should be using a scanning app, but preferably please use some app which is don't use photographs. Rather, please use some scanning app, so that resolution will not be too high and it will be legible. Okay. Fine.
Yeah, thanks.
And also please scan them in portrait, not in landscape. Yeah, but in case you don't like me, then you can always scan it in landscape and upload. Then I will just spend more time converting it to portrait, as I don't have a secretary. Okay, other questions?
Sir,
Yeah.
so in this Jacobi iteration method that we studied in Thursday's lecture, what should we do like in case when we don't have boundary values like x of 1 and x of n?
So you will always have, so if for any problem, you will always have the governing equation plus boundary conditions, right? So you can assume some values here. You should actually assume. Without boundary conditions, you cannot solve for the problem, right? So x0 and xn, you can assume to be some value. Let's say maybe 1 and 2 or 0 and 1 or both 0, something like that.
So yeah, because the question given in tutorial doesn't have this boundary conditions.
Yeah, you can assume. So essentially, you have to assume some boundary condition and then solve for it. Okay. Because without the boundary condition, you cannot solve for a governing equation alone, right?
So it's x1 and xn, na, boundary points?
Yeah, whatever. Yeah, essentially, if you have a, b are your things, then it endpoints. So x of a is some value, and x of b is some value.
Yeah. Okay.
Right. So essentially, if you assume, let's say, x of a and x of b to be both to be 0, then essentially it doesn't matter, because you end up with 1 minus 2 1, and this one when multiplied with 0, it kind of goes away, right? So your matrix will be like minus 2 1, 1 minus 2 1, and so on, all the way to minus 2 1 or something like that. Even if there is a value for xa, that will anyway go to the right hand side, right? If you put it in a matrix form. Yeah, but you're free to assume any value for the boundary conditions.
Like also, sir, like we are solving here a system of linear equations, right, which has the same number of variables as the number of equations. So each of the variables should have a unique value. Now, how can we get a particular answer by assuming some value, like we are doing here?
Say it again. So essentially, you have ax equal to b, right?
Yeah.
Basically, so what I did is basically I fixed the A matrix, right?
Yeah. Yes, sir.
Yeah. Now you can choose whatever right hand sides you want. So once the A matrix is fixed and it is invertible, you can always multiply that with some b and then get an answer for x, right?
Yeah. Yes, sir.
Yeah, and then I can always fix any boundary condition I would like here for x and xb, so that anyway x and xb will eventually make it to the vector b. So it is possible. Essentially, you are solving different boundary conditions. That means you are solving different, let's say, loads or different temperatures or something like that. But the entire problem is not changed, right? The coefficients are all not changing for the given problem. So that's why a is the same. So it really doesn't matter. I can fix it to any value and then calculate the answer. So I thought you can do it, by yourself by any right hand side vector rather than fixing it to something.
Yeah. Okay, sir.
Yeah, makes sense.
Yeah. Yes, sir.
Sir, in that sense that as far as the matrix A is invertible, whatever the vector B is there, the solution will always exist.
Yeah. Should exist, yeah, because it is invertible, and even if b is 0, you'll basically get zeros. That's all, right?
Yeah. Okay, that's a trivial solution.
Yeah.
Sir, see, I have a basic question, sir. See, here what we did, sir, actually our problem started from the finite difference method, how we can apply, and then there was a sequence. There were a number of equations we got from there, the algebraic equations, and to solve them, we got this Jacobi method or the tridiagonal method. So suppose we don't have any finite difference method, but still we can use the Jacobi method if I still have some number of linear equations. That's all.
Yeah.
In that case, I don't need any boundary conditions. I will have those as also my variables.
Yeah, true. That is very true. See, for example, I have, let's say, a system x1 plus 2x2 plus 5x3 equals some 5, and then I have basically 3 equations and 3 unknowns, right?
Yeah.
And I can use this 3x3 matrix to just I can apply Jacobi iteration, even get the answer, right? So if you had applied let's say a finite difference method or some other method, let's say finite element or something, essentially these equations that you get are will already have. So when I say these three equations are already well posed, right? Because I have three equations and three unknowns. So that is what I'm trying to get. Like when the previous student, when he asked, that is what he is trying to say. Without boundary conditions, they may not be well posed because they are still left in terms of XA and XP values, or actually so then they are not well posed. So this is already a well posed problem with the boundary conditions and everything. You can use that as well.
Okay.
Yeah. So essentially, it works for. Only thing is that in this particular case, this happens to be a dense matrix, although it is 3 by 3 because all the elements are there. But we would like to apply it to a Jacobi iteration. We would like to apply it to more of banded matrices as such. You can apply even for dense matrices. Doesn't matter. You can do that as well. Only thing is that the number of elements will be large when you try to put it on the in the multiplications. Yeah.
Okay. Sir, I have one more doubt in that. Sir, can you explain once again, as you have done in the video also, but can you explain once again how to assume the initial value of the X vector?
Initial value, guess value, is it?
Guess value, yeah, exactly. Guess value. In both cases, sir, the banded cases as well as in the fully the sparse matrix.
Dense as well. Yeah. Did I say anything in the lecture? I think I just said X0 can be any guess, isn't it?
Okay.
You can essentially start with anything. See, X0 can be even a null vector also.
Okay.
And it can be even all ones. You can guess anything. Only thing is that essentially the method, let's say Jacobi or whatever method, all the iterative methods. Ideally, these methods, let's say, should yield a solution in let's say some fixed number of iterations, and that should not depend on the that should not too much depend on the initial guess. But I can always say that, okay, I can choose, let's say, an initial guess which is very close to the, final solution, and that way I can actually reach the solution much more quickly, right?
Yeah. Okay.
Let's say for example, let's consider an example of where I have a bar or something which is, heated at one end and kept it like 500 degrees Celsius, something like that, or 500 Kelvin. Okay, the other end is kept at maybe 300, Kelvin or something. Then initial guess, it makes sense to take, instead of 0, you could actually take probably 300 as the initial guess, right? So that you'll get some difference in the final solution, which will probably range from 500 to 300, depending on the source term that is there. So, but it doesn't matter. Even if you take 0, the values will very quickly in 3-4 iterations go to 300. So that should be okay.
Okay. Sir.
Yeah. So usually it doesn't depend on initial guess. So you can take any guess. To be fine, unless the governing equations require it to be some guess, then I think that initial guess has to be chosen in a particular way. But I think we are not going into that area at the moment.
Okay, sir. Thank you.
Yeah, no problem. So yeah, were you able to follow the recursive doubling and the cyclic reduction? So the way we introduced in the class is basically more from a, using the IJ coefficients, using A, B, C and all. So it may look a little complicated, but cyclic reduction is actually very simple. If you work with, let's say, some 3 by 3 system or 4 by 4 system like this, 4 equations, you can easily eliminate the unknowns from the neighboring equations. Okay. Yeah, I hope you are able to follow that. Yeah, okay, there are some questions here. For the question given that I don't think we need boundary conditions. Yeah, probably. What do you mean by saying boundary conditions here? X0, X0 can be formed from. Yeah, so what I mean to say is that your system will basically come out to be, yeah, I don't know if I already explained this thing. It depends on the matrix, right? So how you essentially go about writing it. So let's say the value of X0 is already known, or XA is already known, right? And the value of XB is already known. And then you have to find from, let's say this is 1 and this is n. So you just have 1, 2, n minus 1. Okay. You just need to write equation for these interior nodes and then calculate it. Right. So when you calculate for 1, this will have the coefficient matrix of 1, -2, 1, or I think I put it as -1, 2, -1. Then unless you know what is x0, you cannot really put this -1 times, value at x0 that needs to be put, right? So if we do not put it, and then this will, eventually this will end up in the B term. So you can even have some B term which will take care of it.
So I have a doubt from past week's lecture.
Yeah, that's right.
So
sure.
Where, sir?
Yeah, please go ahead.
I have a doubt from past week lecture. So where exactly do we use OMP set nested in our program? Like at what part do we write it?
OMP set nested. You should put it, in the beginning of the program, right?
Okay.
If you want to turn it on for the entire program, you should put it at the beginning of the program, maybe before the parallel block, parallel region begins, right?
Okay, sir. And I didn't understand that part where you said export OMP nested equal to 1. We have to write in.
Yeah. So see, all these essentially set underscore num threads or set underscore anything, all these commands that are there, right? So they will basically set some variable equal to certain value, right? For example, in the context of set nested, it is setting some variable to true value such that nested nesting is allowed. Similarly, if you set number of threads, it will set the number of threads to be equal to certain value. Now, this is how you do it from within the program, right? By calling a function that is already defined in the OpenMP library, right? So this is from within the program. So you can also do before running the program itself. If you do not want to set these things in the terminal itself, you can set environment variables, right? So if you are using, let's say, a bash shell or something like that, then you can export a value for certain variables, and that will be used when the program runs. I don't know if you are familiar with this, you can do it. Otherwise, you can just set it within the program. That is fine. But only thing is that because these are set outside and these are set within the program, these will get a higher precedence. So even if you set something in the environment variables, they will be overwritten by these values that are set in the program. They will get a higher precedence, right?
Okay, sir.
Sir, I have a question from tutorial 4.
Okay.
Sir, in that, in question 3, we have to find that explicit special derivative, right? Yeah, for that x 7 minus x 10x.
Right.
So so in that question, what we'll do is we'll find df/dx for each point, right?
Yeah. You would find df/dx. Basically, df/dx will be an array.
It will be an array of n points, where n is b minus a divided by number of points.
Right.
I mean that delta h thing.
Right.
So after computing let's say after computing this entire array of df/dx, what will be the actual differentiation? I mean, for that entire range, we have to sum it up or something like that. I mean.
So you take after you calculate this, what is the?
Like what will be the derivative for the whole range? Like.
Yeah, I mean, essentially, see, what we have is basically we have a certain values of x, right?
Yeah.
These are your x values, and some function is given. So function is, instead of being continuous function, this is kind of discrete, right? Yeah, we have given these values.
Yeah.
Right? You would find a derivative of this function. So let's say derivative is, something like this. So that's your, now you get derivative instead of a continuous function. You get it only at these discrete values. So whatever this array that you have computed, if you connect all of them with respect to, you know, x, then that is your df dx.
Oh, okay.
Isn't it?
I got it. Yeah, I got it.
It's still the numerical derivative, right?
Okay.
So if you find, I don't know, I forgot the function. I think I just gave some 7 minus x tan x or something, right?
Yeah, 7 minus x into 10.
7 is just there for, you know, it will be 0 anyway. So you have minus x tan x, and then you just, so you can also calculate the exact value. Now the exact value may not correctly match with this analytic, then the analytical value may not exactly match with this numerical derivative. There might be some error, right?
Yeah.
Now that error is what is you connect it to the order of accuracy, right?
Okay.
Because
So,
you have of the terms, and that is the reason. And then if you keep taking this grid to be smaller and smaller, it is believed that this error will reduce, right?
yeah.
Yeah, so go ahead.
Sir, I have a question.
Yeah.
Sorry, yeah, you can continue.
Okay, so sir, is there any, formula or something for calculating the actual derivative from this thing?
The actual derivative calculate just UV formula, right?
Okay.
Yeah, just x tan x, just take a derivative using u and v, d by dx of uv.
Okay, so by this, so this is the answer, that we have calculated as an entire array.
Yeah. So this is df dx of array final answer. You can plot it, calculate it. Yeah.
Oh, I see. Yeah, I got it.
Sir, I have a question on parallel for.
Parallel for, okay.
So we have, let's say we have #OMP parallel, like a block. And inside the parallel block, we have 2 for loops, each of which is enclosed in OMP for. So, and in the first for, no, not like this. So I think you just, inside the parallel block, you have 2 for loops, and you have OMP for both. And the first, we have a no wait clause in the first one.
First one you have.
Yeah. So if one thread, so obviously that means that in the first for loop, one thread will be the first to leave that for loop, right?
Yeah.
And it will come to the next for loop. So what happens when it comes to this next for loop? Does it start executing by itself over here, or does it again branch out into several threads?
No, here there is no branching. Okay, it doesn't matter whether you have no wait or not.
Okay.
It doesn't matter no wait. Okay, so essentially what I mean to say is your branch forking happened here, right?
Right.
Based on your number of threads that you have set here, forking has happened here. So there are no new threads that are created. Let's say you have forked into 4 threads, then only those 4 threads will execute this thing. And if you had given a no wait, whoever finishes first hopefully will start executing this one, right? That's all. But you still have only 4 threads for the entire block.
Right, but when you say OMP for, it means that the existing threads will be, the work will be divided over the existing threads.
Yeah.
Okay.
That's right.
So when it reaches the second for loop, then there is only one thread that is present at that for loop, right? The second for loop. Whatever has left the no wait clause is now arrived at the second for loop. So how does the second for loop know how many threads to actually divide the work by?
Okay, the number of threads probably it would know from this being in the block, I guess.
Okay.
Isn't it? It just doesn't know. So it knows how many threads are there. Once you enter this thing, it knows that how many threads are there. Assuming that there is no, barrier at the beginning. I think this question came up in the last discussion as well. So the T0, let's say if you say T3 finished first, and once T3 comes here, it should actually go and start working on its part of, for within this thing.
Right.
Yeah.
Okay. Right. So there's an implicit barrier at the first statement itself. #OMP for.
Yeah, I don't think there is a barrier as such. I guess because the threads. I mean, I don't think there's a barrier at the beginning of the statement initially. Because the threads will execute this in any order, and then once they come here, they would take up the their task. I don't know. I have to check that. Maybe Rupesh can add if he knows about it.
Yeah. Yeah, I don't think there is a barrier there. At least the documentation doesn't say that there is a barrier.
Yeah.
At the start.
So is it like the work is already lined up for each thread, and then once it finishes its previous work, it immediately starts the next one? It's like something is already lined up to work for it.
Yeah, I mean, if you say no wait, it kind of behaves like that. In fact, that should be the case even if you have, let's say, dynamically changing number of threads as well. Because if you give maybe no wait, I think it will come and then it always knows how many threads are there and they will start executing that portion that belongs to them, right? I mean, whether it's right or wrong, that's a different question. But according to these commands, I think it will start executing. Yeah. But what about barrier for the first loop? At the end here, there will be a barrier, isn't it?
No, because we have the no wait clause. There's no barrier.
No wait, then no problem.
Relax it.
Yeah.
Sir, I have one more question.
Yeah.
Sir, let's say, let's say we want to parallelize two loops as we have in our tutorial for let's say for addition, matrix addition.
Yeah.
So in that case, can we write like a hash pragma OMP parallel, and then inside for two loops, hash pragma OMP4. But like when I tried it, it was giving some error, like it is saying that deep nesting is not allowed, even if I have set the nested that variable as true.
Did you say?
Yeah, and when I try that directly, I mean, when on each loop I write that hash pragma OMP parallel for each loop with nesting as on, then it is working fine. So I am wondering if that is allowed or not. Like first thing that I told.
You mean to say if you just write hash pragma OMP for and put the parallel outside, it is not working, is it? Or you have nesting inside?
Yeah, the first one that you said, we place for on each loop and the parallel section is like above everything.
Yeah, there is no nesting here, right? There is no nesting here. It is always this is
no, sir, not for this, sir. I am talking about that
matrix
different question.
Yeah,
multiplication.
Matrix addition or multiplication. You have basically two loops, right? You have for I loop and for j loop, right? Isn't it?
Yeah. So what I was doing is I was placing OMP hash pragma OMP parallel. Hash pragma OMP 4 on each of these both loops.
Okay.
And parallel section was outside enclosing these two loops.
Okay, so if you do both,
so it was giving some error here, like.
Okay.
But if you do in other way, like remove this above parallel section and on each loop we write hash pragma OMP parallel 4, then it was working fine, even if there was not nesting.
Yeah, I mean, you first of all, let's see the difference between these two. I think you understand the difference between the two implementations, right? In the first one, so in the second one, essentially you are doing a nesting, right? So you're essentially spawning, let's say 3 threads in the top and 3 threads. So you're essentially spawning 9 threads, right? You're forking 9 threads.
Yeah.
The second implementation. Whereas in the first one is troublesome actually. Let's see. So you basically have forked into, let's say, 3 threads, T0, T1, T2. Then here, this is kind of, it's good that you asked. So T0 comes here, and then I don't know what is the behavior here because
it is just giving error here, compile time error.
Yeah. I think I don't know. This is. Do you understand the problem with this?
No, actually I thought about it, but I thought like it should work because what I was doing is
maybe you have to,
on
yeah, if you want this kind of thing to work, then you probably have to, what do you call, there is something called unwrap or something. Is it a function like that, or unwrap the loops, or what is it called? There is a corresponding name for that.
loop unrolling or something like
Yeah,
that.
unrolling. Yeah, I think unrolling or something you have to do, because it. I think this is probably not a good idea, isn't it? Then if you do an unroll, then I think it will make, remove I and j, which go from, let's say, 1 to n, and this will make a a single loop index, and then then all the three threads can work in parallel on that thing, right?
I mean, so we need to unroll the inner loop and just parallelize the outer loop, something like that.
No, I think once you unroll, you are basically unrolling both the loops, I guess, because this I don't know. Maybe someone else can comment if they have an idea.
Okay.
Yeah, just to add to what Kameshwar was saying, I think, I mean, see, the three threads here are already created. So when we have hash pragma OMP for I loop, there is just a distribution of work that is happening. There is no creation of threads, right? And so when one particular thread is reaching the hash pragma OMP for the J loop, I mean, there is no forking happening really here. So one thread is, I mean, unable to share. I mean, not unable to share, but it looks a little odd that one thread is only going to reach, and that thread is asked to share the work, and that's the reason why OpenMP is probably giving the error. Does that seem reasonable, Josh?
Yeah, sir. Yeah.
Yeah. In contrast, if you had hash pragma OMP parallel also for J, now at this stage, then possibly the nesting should start working.
Yeah.
Yeah. Yeah.
Yeah. Okay, there are some questions here. Collapse statement. Yeah, collapse maybe. Okay, we have nested for loops without forking it, say something like pure nesting model. Okay, yeah. Yeah, it's a good idea if you kind of, if you jump into these problems, it would be a good idea to just share it on the discussion forum so that everybody might benefit from it. Of course, you can also discuss it on the Q&A session as well.
Kameshwar, I have one question on one of the lectures. It might be basic for the students, but nevertheless, I'll ask. So this, when we say that A matrix gets converted as, let's say, M minus n, where M is invertible or easily invertible. And then we have, so the term that comes in later is, when you rearrange the terms, is M inverse B.
Right.
So this, does it, I mean, we have probably different methods which work with the dense A and sparse A, but does it also matter somewhere if B is sparse or dense?
B.
Because of this stuff, if B is sparse or dense, does that matter in any application like this, or?
No. Usually B is always dense, actually.
I see.
Yeah, mostly B will have the right hand side usually will have terms because mostly we will not optimize, at least at the programming level, we will not optimize this matrix multiplication as such.
Okay.
So if let's say this becomes, I think eventually this becomes D or something, the corresponding right hand side. So this is always added when you do the Gauss seidel. So in case if it is, so there is no multiplication involved, so it doesn't really cost much there.
Okay.
Yeah.
Sure. Thanks.
Yeah.
Sure. I have a question. When you have a function inside a parallel block, like OMP parallel, and you have a function called that, and inside the function, which is outside the parallel block, like when you define the function before the main, there you have a loop in the function. and the loop is bounded by again like an OMP do or OMP for. So now this function is going to be called. Let's say we have 10 threads. The forking happens and you have 10 threads. Function is going to be called 10 times, right? And each of the variables in the functions will be made private to each thread.
Yeah.
Now, if you have, let's say, a work sharing construct in the function, like the for loop that I just mentioned, or if you have even OMP sections, or if you have OMP work share, those types of things, then inside the function, then how is each thread, which cannot access a variable from other threads, how is the work going to be shared among different threads?
Okay, I am
inside the
afraid
function.
you have to probably repeat the question. First, I will repeat it and then I'll tell you where I don't understand. So basically, we have created a pragma parallel here, right?
Yeah.
And then there is a function called below this. Basically, this function will be executed by all the threads, right?
That's right. Yeah.
All the threads will execute this thing. And then what is inside the function? So you have now the function with some return type, some arguments, okay?
Yeah. Inside the function, let's just say you have a loop, you have a for loop, which is also parallelized.
Okay, so basically here we have pragma OMP for, right?
Yeah.
That's
right.
Okay. Yeah.
Yeah. So the question is, now all of the variables in this particular function, even if there are some variables before the hash pragma OMP for statement, all of that is going to be private to each thread.
Right.
Right. Okay. And so now, since this function call is private to each thread, only one thread is going to be arriving at pragma OMP for.
No.
Like per thread.
All threads will call
per
this.
thread. All threads will call, but the thing is, you're calling the function 10 times, right? Because if you have 10 forked threads in the previous block, then you're calling it 10 times.
Yeah.
So each thread is actually arriving at hash pragma OMP for.
Yeah, right.
So how is the work shared?
No, once they come to this first statement, all the 10 will divide this whatever n by 10 and then work from here, right?
Okay.
So think of a statement. For example, let's say, from your example, I will remove this function. I don't have a function. Okay.
Okay.
I have, let's say, an inline code where I have some variables declared, and then I have a pragma for, right? Then it will be the same way whether you have a function or not, right?
Yeah, so that's what I wanted to ask, if it is actually the same, because in this example that you just stated, that's actually straightforward, because this is what we learned in the course.
It will be the same even if you have a function. Now the only issue is that, like, as we saw in the integration example, if you again put a reduction clause or something on the left hand side here, then we don't want to or a critical statement here or reduction clause, then function, instead of being called in parallel, like we are discussing, all of them will call it simultaneously. And if you have a reduction and something or a critical statement, then function also will be called serially. That is where the performance penalty will come into play.
Okay.
Yeah, but it should be the same. Like at least whatever you have explained, it should be the same behavior even if you don't have the function.
Okay. All right.
Yeah, other questions. Is everybody fine with the assignment timelines I suggested? So I don't know, maybe more people have joined. No, 36 only. So, and then I'll also send out an email regarding assignment and exam. So exam, we'll have it on Tuesday, 16th of March from 11 to 12, 11 to 11:50 actually. And then assignment I will post by Monday at max, and then you will turn it in by 22nd or so. I hope that's what I said before. Yeah, okay, it's here. 16th March, and then assignment by 22nd March. Okay.
Sir, could you go to the page where you mentioned about the nested for loop?
Where?
The previous page where you mentioned about the nested for loop.
Nested for loop, huh?
Yeah, below.
Hold on. Here, yeah.
Yeah. So in the innermost for loop, you're putting parallel for, right? Because if we put this for, it will not make sense. But like, say, it's executed by T naught. Like after it sees a parallel for again, how will it again fork from one thread?
Can you please repeat the question?
And so let's say the outer for loop is distributed across 3 threads.
Yeah.
And then the inner for loop will be taken by one thread, one of the threads, right? Like.
Yeah.
So how will it again fork from a single thread after seeing parallel for again?
Yeah, so if you see parallel for, then it is logical to fork, isn't it? Because whatever thread that comes here, let's say T0 will again fork into whatever 3 or something like that, right? And then whenever T1 comes, it will fork into more and so on.
Okay.
Right?
So also one more question.
Yeah, sure.
I actually didn't understand how we are like avoiding loop carry dependencies in the recursive algorithm, doubling algorithm, because also have like dependent terms, right?
Can you please explain? So you didn't understand how we are avoiding recursive doubling, how we are avoiding loop carry dependence in recursive doubling algorithm, is it?
Yeah.
Okay. Let me see. Okay, so what we are trying to do is, so the gist of the algorithm is basically you have, we started off with this tridiagonal matrix, right?
Yeah.
Okay, so what we tried to do was essentially push the diagonals one row or one column away from the main diagonal in one iteration, one step. So after one step, you have basically zeros on the sub and super, and then the original main diagonal, upper diagonal which was here is now moved here, and then the sub diagonal which was here is now moved here. Okay, and then you are essentially continuing this process until your final iteration, which is log n base 2, as I discussed, and until your final algorithm where you essentially just have a diagonal matrix, right? And how we are doing this is basically for, let's say, for any equation I, you have dependency on xi minus 1, xi, and xi plus 1, right? Then you are writing an equation for you are essentially extracting value for xi minus 1 from the I minus 1th equation, and then xi plus 1 from the I plus 1th equation, right? And then substituting them into this ith equation. And as you can see, xi minus 1 equation will depend on xi minus 2, xi minus 1 and xi, and xi plus 1 will depend on xi plus 1 and xi plus 2, right? So I minus 1 equation, if you try to express xi minus 1, it will be in terms of xi and xi minus 2, and xi plus 1 will be in terms of xi and xi plus 2, right? Now you substitute for these two into the ith equation, then your dependency on xi minus 1 and xi plus 1 is gone. Instead, now you are introducing xi minus 2 and xi plus 2, which is basically nothing but this shift. So this dependency from I minus 1 is gone, you're getting it from, I plus 1 is gone, you're getting introducing I plus 2. Similarly, if you have an element here, I minus 1 is gone, you're introducing I minus 2, right? And the same is repeated until you end up with a diagonal matrix. Now the idea is that all these computations we are doing here, all these can be done in parallel, right? At any iteration, all these computations for all the elements can be done in parallel because they don't depend on they already have all these values, right? So at any step k, all the iterations can be parallel within that iteration.
Okay, sir. Okay, sir.
Yeah, and then we are of course adding some memory overhead because you are trying to allocate more variables, but that's not super large. I mean, it's kind of tenfold because let's say you have 3 rows, right? You basically have A, B, C. Each of them are of the order of, let's say, n, right? If you consider n by n matrix, Then we are going for log n base 2 steps, and then you have to allocate so many variables for k, right? We are writing a, k, b, k, and okay, so that I think this probably can be optimized to be reduced in memory, but I think that's not too much because we're not duplicating the entire matrix. Only the 3 diagonals is what we are duplicating for all the steps. Probably that can be even overwritten. I would look at the algorithm. Is it does it make sense? Are you able to relate it? Yeah. Maybe if you go back now and listen to the lecture, it will be probably a little more clear.
Thanks.
Yeah. Thank you. Any other questions? Okay, if there are no more questions, then shall we call it a day? I think few people have joined late, I guess. Yeah, so we just decided that our quiz 1 will be on Tuesday, 16th March, and from 11 to 11:50. That is online. So I will upload the question paper a few minutes before 11, and I will also be online, okay, on Google Meet completely throughout the exam. If you wish, you can log into Google Meet, but it is not mandatory. Okay, only in case you feel like you have a question or need a clarification, please log into Google Meet during that time, and then I'll answer. I'll also hopefully provide mobile numbers of the TAs. Okay, so in case you have difficulties, you can call them, but please try to upload the solution only on Moodle. Okay, please do not email me. No email, please, because one thing is, if you do not submit on Moodle, I won't be able to grade it, and your showing a grade for you will be difficult because I cannot create an entry for you. You have to create one so that I can grade it. Okay, so if you send me an email, I'll not grade it. Reason 1, I don't have secretary. Reason 2, I cannot manage all these things. Okay, it has to come through Moodle only. So please upload on Moodle. There will be some time after which it will cut off also. I'll send those details later. I will send you instructions also. It should be fine. I think it should be straightforward and peaceful. Okay, I have done it before with other courses during lockdown, so it should be fine. So I'll send instructions and just please follow them. That's all. Okay. All right. So if there are no more questions, then shall we call it a day?
Yeah. Thank you, sir.
Okay. All right. Thanks, everyone. Have a good weekend. Talk to you next week. Okay. Bye.
Bye.
Stop recording.